Everyone, thank you for taking the time to join us today for this discussion on design considerations for a high-resolution lens. I'm fortunate to have engineer from Edmund Optics, Eduardo Gonzalez, is here, as Dave mentioned, and we really appreciate you taking the time to join us today. As an overview of how we'll handle the discussion, I'm going to first start out and give a brief introduction to Synopsys and the Synopsys Optical Solutions Group. I'll introduce a few of our software products, and then I'm going to give a very brief overview of Code 5 optimization, just a few charts. It'll take about the first 15 minutes of the presentation. And then I'm going to turn it over to Eduardo, where he's going to describe and explain the details of this design discussion. As Dave mentioned, you can type questions into the chat, and we can then handle them at the end. So first, let me start by introducing our company. Synopsys has been around since the middle 1980s. We are actually the 15th largest software company in the world. The start for Synopsys was in electronic design automation. So that's the main types of tools that are used to design IC chips. But since that time, Synopsys has expanded reach in IP and security, and as well, obviously, into the optical world. About 10 years ago, they started in looking at the leadership in Synopsys looked at the ties between hardware and then also modeling and simulation. And that's how we are now fortunate to be part of the overall Synopsys team. You can see just some metrics here from we have over 14,000 people. Fiscal revenue 19 was about 3.4 billion. And we do have people working in our team all over the world. So it's a really great company producing software for engineering projects and problems in a wide range of areas. And we are happy to be serving you as our customers. So the Synopsys Optical and Photonic Solutions teams have been part of Synopsys starting since about 2010. You may be familiar with Optical Research Associates. The team at ORA was around since the early 1960s, actually, as an engineering services team, which you can see over here on the right. But also the makers of Code 5 and Light Tools. Code 5 was the first commercial product from ORA, and it actually, I'm happy to say, just had its 45th birthday, I think the beginning of August. So it's been out and being continuously developed. So as I mentioned, so ORA has been doing optics and software for many, many years. And we have had a great success in helping our customers develop their solutions for engineering in a wide range of areas. We have tools that address imaging and illumination design. Code 5 and Light Tools represent those tools. Lucid Shape is our automotive lighting design software. And then we also have the Photonic Solutions software tools, our soft photonic device tools, which is used for passive and active photonic device simulation, as well as photonic system tools and the Photonic Integrated Circuit Design Suite. As I mentioned also, we do have an engineering services team that provides expert design services for both imaging design and illumination design. The team has been together for many years and has provided over 5,000 completed projects, which have been delivered for use in production. We have many different tools that have been brought to market to do design optimization, virtual prototyping, and tolerance analysis. And the beauty of having a long-standing team and having been working together for all of these different products, we have been able to continuously develop and innovate solutions that bring you as engineers strong solutions for your work. So Code 5 and Light Tools optimization are very powerful tools for use in optical design or illumination design. Similarly, in our Lucid Drive products, or also the Light Tools products for automotive lighting. And many of you who are here today to hear about Code 5 are aware of the efficiency of Code 5's tolerancing. If you haven't been introduced to Code 5's fast wavefront differential tolerancing, it's very, very fast and accurate methodology for tolerancing your optical designs can be done so quickly that it's easy to do early in the design process and allows you to get a good feel for what are the tolerance drivers in your systems. Additionally, Code 5 offers expert tools which build from that expertise in our engineering team to help you succeed as a designer. Tools like the Glass Expert and the A-Sphere Expert are leveraging the engineering expertise to help users who haven't had quite so many projects to experience the use of Code 5 to succeed even more easily. In the end, our focus has been on technology innovation and accuracy to help you to do the best work you possibly can do. So, as I mentioned, I'm just going to briefly talk a little bit about Code 5 for imaging optics. Code 5's birthday, as I said, was August 1st and from 1975, and it's been in development for some of the most challenging optical design problems that are out there in the world today. People use Code 5 in virtually every industry. It's been one of the most fun things about joining the Synopsys team I've been able to see and learn from you as our users the various types of problems you're trying to solve in a wide range of industries. You can see some examples here, aerospace products, automotive products, microlithography, things that are used in automated or assisted driving systems. There's just a very wide range of instrumentation and optical systems where Code 5 plays a part. And it's really a fun thing to be able to work together with our users to help them succeed in bringing these types of systems to market. Light Tools, which came into being in 1998, I believe, is our flagship illumination product, and it's used in also a very wide range of optical simulations and virtual prototyping. You can see some examples here of the kinds of systems you can do, sort of a puddle lighting or interior car lighting. You can think of Light Tools for everything from projectors or flat panel displays to light pipes, as well as simulating medical instrumentation or street lighting. There's just a very wide range of product capability that Light Tools brings for our users. And especially setting it apart is our optimization and tolerancing that are available for freeforms and very unique types of illumination problems. Additionally, we focus highly on our software quality in Synopsys. Synopsys being such a large software company and focusing on the expert testing of the different aspects of the functionality of the software. So we definitely make use of software development and configuration management in a formal way. We have thousands of test cases that are performed on the software on even a nightly basis, weekly and nightly. This helps us to really confirm and ensure the reliability and the accuracy of the software for your use. The additional thing is we can use these things to alleviate the need for our users to be faced by damaging or difficult bugs, as well as those types of aspects of benefits from the software. We also have an extremely complete documentation catalog. Code 5 I've been using for many years and has one of the most thorough and very well explained sets of documentation for any types of modeling or analysis that you may want to do for your imaging design. In addition to those benefits, we also offer an expert technical support to respond to your needs as users. We are focusing all the time on a daily basis on quickly answering your technical support needs, either via email or also via telephone calls when needed. We can set up WebEx or kind of view each other's screens and work together to get you past any hurdles you have with the software. We have an experienced team of optical engineers with master's and PhD level degrees in optics. And we also have a dedicated customer education website. Our portal has a wide range customer, you have access to the customer portal and can get access to example models, video tutorials, wide ranges of all of our training materials and other resources, user supplied and also internally developed macro scripts to help make your work more efficient. Additionally, the tech support team provides on-site and in today's world, a lot of online training seminars for hosting the abilities for different levels of people and offering a spread out time frame for people to do remote training to gain expertise with the software, as well as providing expert customer-focused input for the documentation and product enhancements. So when you have a new need or the software is coming up short for your needs, we are able to interact with you and learn those requirements and take those back to the development team. Last, I would like to mention that we do have our team of 9 engineers. There are 6 PhD engineers with a very broad range of expertise in imaging, illumination, and optical systems engineering. We have people who focus on aerospace and those types of applications, consumer electronics, consumer optics, these types of things. We have people doing focus on illumination design, and we're really able to focus on your needs for solving design problems. As I mentioned earlier, there have been over 5,000 custom design projects, either currently or formerly in production. And it really helps us as a software company to provide a unique user perspective on the real engineering projects that people face so that we in the development of Code 5 can enhance the product's capabilities and technical strengths. So for my last couple of minutes, I do want to give a more specific overview of optimization strengths in Code 5, and I think this will lead nicely into introducing Eduardo's portion of the discussion, the main portion of the discussion, where he'll talk about his design. So that's the next few moments that I'll spend just a few charts talking about this. If you're not familiar with Code 5, or if you haven't used it in the past, one of the real strengths of Code 5 is the automatic design capability. This has been one of the strengths of Code 5 from the very beginning. It's a very powerful damp least squares methodology for optimizing. We have some very unique internal proprietary methods for handling Lagrange multipliers for exact constraint handling. This is something that's challenging to do, and as far as I'm aware as a user and having been an optical designer since starting in around 1995, I've not seen it handled as well anywhere except in Code 5, where it allows you to really meet your exact constraints as needed while still finding the ability to reduce your errors and aberrations to make better performing lenses. This is, as I mentioned, really one of the main strengths of Code 5, and something that if you haven't had a chance to try, I encourage you to try a demo and a trial of Code 5. Additionally, as part of doing your design work, we have a very powerful global synthesis algorithm inside Code 5, which allows you to compute a wide range of design forms with unique configurations that are going to meet the constraints that you've set up for your systems. This is really a powerful tool to use when you have systems with multiple configurations or zoom positions or more complex systems. You do have scaling execution times, but computers today are very fast. So it's a great way to do an excellent starting point generation run, or also a great way to verify that your final design form is really optimum, both from the standpoint of performance, but also from the standpoint of manufacturability. And this is something that routinely our engineering services team uses because of that last point. They're able to make the systems more manufacturable more easily. And I think that ties into what Eduardo will talk about in his work as well. The last comment, really, this brings out a key highlight of one of the things that we offer inside Code 5. We offer a few ways of desensitizing your design, and these are capabilities that have been around inside Code 5 for many years. We have some ability to directly control the sensitivity of each surface using a sensitivity error function constraint. But we also have the ability to build a completely separate component of your error function. The target of each error function is usually a quality metric, and you want to make things better by driving the error function lower. So we have on the left-hand side an example of a global synthesis run where on the vertical axis you see the as-built wavefront error, and on the horizontal axis you see the error function. And this smaller is better here. So the software is trying to drive things down here, and it gets a value of below 0.1 for this red system. But you can see the as-built error, the best error function is giving about 6 waves RMS. It's not anywhere near as good as this as-built system. And really what you would prefer is to have the software find more of systems like this, where you have a low as-built performance. And so by using these kinds of sensitivity constraints, either indirect or direct constraints, depending on how you want to set up your design in Code 5, you can see a result more like this side, where here were the initial plot of the systems. When you use that sensitivity as built separate error function component, you see a system out here towards a value of 1 for the optimization error function, down here to a value of about 0.5, but they all have far superior as built performance to those systems that were far over in terms of low optimization merit function. These are great as built, and that's what you really want to strive for, and Code 5 really helps shine by letting you use global synthesis and these optimization tools to achieve that. So without further ado, I'm going to turn the rest of the discussion over to an optical engineer who's making use of Code 5 in his work, and he's going to discuss what he's doing. So I'm going to go ahead and stop sharing.
Okay.
And Eduardo, I really appreciate you taking it away.
No problem. Am I a presenter now?
You will be right now.
Okay. So here we are. Thank
Perfect.
you very much for the introduction. And let me get that away for now. And set up the laser pointer. Thank you very much for the introduction, Matt. As you said, I'll be discussing how I use Code 5 to design a lens for a new sensor format, which also helped launch a new family here at Edmund Optics. And by new family, I mean new lens family. A little bit about myself. Again, my name is Ed Gonzalez. I've been working for Edmund Optics for over 13 years now. I started off in quality assurance, worked my way up and did some test bed design and assembly. Went into manufacturing, where I manufactured spherical and aspheric optics. Unfortunately, I did not get any experience with conventional polishing or grinding. All of my experience was with CNC machinery for the spherical and obviously the aspheric optics. I've gotten the opportunity to be an optical design engineer here. I've been doing that for 5 years. While I've been here, I've done design and analysis of lens systems and components. I've done analysis for my peers as well as the lenses that I designed myself. I am fluent in both Code 5 and Optics Studio, but in the beginning of my career, I used Code 5 primarily for the real-world manufacturing analysis. So this lens presents the first time I was able to design a lens from beginning to end using Code 5. So I'm very excited to show you guys how I did that. A little bit about Code 5. Once again, it is great and it's used for tolerancing and manufacturing analysis here at Edmund Optics. It is also a very good optical design software. It's very robust. It's fun to learn because it presents you different ways to do the same thing depending on what you would like. I, for one, was taught to use the command window a lot, but Matt has introduced me to the benefits of using the user interface more. And the best part about that is even if you use only the user interface, but you would like to write a macro, the command window presents you the commands that were used when you were trying to do something in user interface. So you can write custom macros if you would like. And as I mentioned, this lens that we're presenting was designed from beginning to end using Code 5. So what kind of lens was requested from me? It is a 75 millimeter focal length with a primary working distance of 750 millimeters. And the reason we use the word primary here is this lens was expected to work at several different conjugates as well, with different resolution requirements. For the purposes of this presentation, we're going to concentrate on the 750 millimeter working distance. The image size is a 28 millimeter full diagonal, and that is what makes this lens special when we're talking about the large format. A 4/3 inch sensor is about a 22.5 millimeter diagonal. So now we have over 5 millimeters difference in the diameter, which presents some challenges when it comes to aberrational content. This also presents a challenge, which we'll go over in the next slide, for the mounting scheme, as 4/3 inch is typically used with the C-mount mounting scheme. This lens was requested to have a resolution of 55 line pairs in the visible with a 40% contrast. So that 40% is for the nominal design here. What this does is it allows us some room for a drop in performance when we apply the real world tolerances to this lens. So 20% is the threshold for the passing or failing of a lens at 55 line pairs per millimeter after it's been evaluated for as-built performance. Finally, the lens has to be less than or equal to 92 millimeters in length. That is from the front of the metal to the flange. So a little bit about the problem that I was saying we would have using C-mount with the Sony APS-C sensor here. It's that the bore of the C-mount is 22 millimeters, which is 6 millimeters smaller than the full diameter of the image sensor here. So this would present some problems in that we would have some extreme ray angles coming onto the sensor, which could cause some issues. And we also have a good chance for vignetting to occur in our design. So in order to address this, we used a hybrid mount, which is the TFL mount. And I am calling it a hybrid mount because it is much larger in the bore diameter, which allows us to use larger elements and control those ray angles. But it has the back focal distance of a typical C mount, which is good because the step up to F mount would have a almost 47 millimeter back focal distance. So you're saving over 29 millimeters in just package size with having a larger sensor, but having this back focal distance. Now, while this is a really good trade-off, we still have the challenge of having the shorter back focal distance with this wider field of view. And that's what we're getting here is the ability to have this larger image here and hopefully get the best of both worlds. So I'm going to go through the design process that we use internally here at Edmund Optics and that I followed. There are different gates that we have to go through. The first gate being the feasibility gate. And this could be different things depending on your customer. It could very simply be, is this lens that I have specified possible for you to design and manufacture? And that's just a yes or no. It could also be a trade study where the customer wants something, but they are flexible, and you can show them different solutions to their problem with different compromises for the designs. So how are we going to get there? Which is the first step. Well, if possible, you choose an existing design that is close to what you need. I have access to a large lens design library at Edmund Optics, so I'm very lucky in that I have a lot of examples I can choose from. I realize a lot of you don't have that opportunity, So I'd like to point out that there are databases that are available that you can purchase for starting solutions. And also there are some books you can look at. For instance, as you can see on the bottom left, Lakin's Lens Design or Smith's Modern Lens Design can give you some good starting solutions depending on what you need. Since I have access to previous designs here at Edmund Optics, I chose our part number 86574. And what that is a 50 millimeter focal length lens imaging onto a 4/3 inch sensor. The reason I chose this particular lens is because the focal length to sensor size ratio is similar to what I'm going to be designing for, which means that my field angles are going to be similar as far as the aberrational content. So what I did was I scaled this lens up to 75 millimeters, then made the necessary changes to working distance and my image size to have a solution that I can start writing a merit function for. So for feasibility, I'm trying to have the largest available solution space that I can come up with while keeping it realistic. So I write a merit function that loosely controls the mechanics of the elements. I put lens here, but I mean specifically the elements. And by that, I mean the diameters, the center thicknesses, the air gaps between them, and the edge thicknesses. For my particular design, the focal length, the working distance, F number, and waveband are all rigid requirements. This is not always the case when doing a design. It happens to be the case for the design we are talking about here. And then finally, if you're in the feasibility portion, if you are unsure of the design form or you're simply curious, and most importantly, you have the time to do it, Global Synthesis is a very good option to provide you a lot of solutions so you can explore the design space and see if maybe there's something you didn't think of. When you have done your optimization, whether it was global or something local, then you review the results and see if there's a solution that looks feasible. And here at Edmund Optics, that is then reviewed by my peers and our principal engineers to see if it can go on to the next step. That next step is the preliminary design process. And in that gate, what I do is I take that feasibility lens and I try to make it more realistic by then making sure my center thicknesses and my edge thicknesses aren't as loose as I allowed them to be before so that they're manufacturable and more affordable. After that is done, then I run a manufacturing sensitivity analysis, which was mentioned earlier with the wavefront differential analysis. This is not a sensitivity of the metal and the elements. This is simply the sensitivity of the elements being manufactured. And this is important because if you have a lens that is very sensitive without taking the mounting scheme into account, then there's a good chance your performance is only going to get worse. So you're either going to have to design the sensitivity out of the lens, or you're going to have to go and find a different solution for your problems. If you have done all this and everything works out well and your design is not sensitive, then you go into the critical design process. And here, an optomechanical engineer takes a look at your lens. They design the mounting and housing for it, and then I apply both the element manufacturing tolerances and the metal manufacturing tolerances to the lens and use Monte Carlo generation to analyze the real world performance and make sure that it is performing as we have predicted, or we hope. So I ended up having the time and ability to use global synthesis for the feasibility of this lens. I was pretty sure about the design form that I was going to use for this, but I was learning how to use Code 5 and wanted to have a little fun, number one, but also I wanted to see if maybe there was a design form I did not think about or see that could lead me down a different path that would be better. So one of the very interesting things that global synthesis has is this discrimination factor. So what this allows you to do is control whether or not you want your solution for the global synthesis to be close to the design form you already have or to vary greatly from it. So if you have a discrimination factor of less than 1, the closer, the smaller it gets, the better chance you have of getting many solutions with various form factors. And this is great, but now you have a lot of solutions to go through. If you have the discrimination factor go over 1, well then now it's going to keep it to the same design form. So for instance, you chose a double gauze, it's going to be something that looks very much like a double gauze for all of the solutions. So you'll get less solutions here, right? But now you're concentrating your design space down, which some people want. I, on the other hand, went with less than a 1 because I wanted to see what was available there. Another important tool is the reduced tolerance sensitivity parameters. So this isn't a button that you just hit and it works. You have to apply tolerances to the lens before you can do this, but luckily Code 5 comes with default tolerances that you can apply to your lens very easily. We'll go over that a little bit later. Now, importantly, and as I mentioned before, both of these can be done via the user interface or the command window. And if you want to learn how to do it via command window or write some macro for it, just use the user interface and take a look at your command window history, and it will tell you what was written in order to accomplish this. For my global synthesis, I loosely controlled element aspect ratio and the ray angles. The aspect ratio was to keep it realistic for manufacturing purposes. The ray angles were to keep sensitivity down because that's how I happen to control them. So I was discussing the aspect ratio here and also the loose mechanical tolerances. So what I controlled were edge thickness, as you can see here, the center thickness, and the outer diameter of the lenses. To control them more tightly, I ended up controlling aspect ratio, which is the outer diameter to center thickness ratio for a positive lens, or outer diameter to edge thickness ratio for a negative lens. For the global synthesis, as I said, I tried to keep things looser so they're not as restrictive. I tried to keep an aspect ratio between 3 to 12 when I was doing this design. For more information, I have a link here at the bottom of my slide where my colleagues go over the aspect ratio and some of the manufacturing tolerances and restrictions that I've used, but they do it in more detail. Also, importantly, I've controlled the concentricity of the lens. And what concentricity is essentially is I'm keeping the two radii on this negative lens separate from each other. If they are concentric, that can cause a lot of problems for your manufacturing cell and make the lens very difficult to center. And that is simply because if these two radii are concentric, and now they happen to have some wedge and one is up here, the amount you would have to roll this lens in order to get your optical and mechanical axes to match up is going to be very large. As a rule of thumb, I try to keep them at least 2 millimeters apart. This is my rule of thumb. It can vary between designers, and manufacturing capabilities vary, but since I know what we are capable of in Edmund Optics when we manufacture our lenses, I keep it at a 2 millimeter distance between the two radii at the very least. So I ran the global synthesis, and what you get is a text listing of all of the results that you had with the error function value listed next to each of those lenses. I ended up with over 100 for this result, which I thought was pretty cool until I was like 15 lenses in. Then I just pulled the top 10 for the error function value, which is the lowest 10 there. Took a look at them very quickly to see if they looked realistic or not. And then I came up with 2 that I wanted to show you for this presentation. So the first thing you can look at here is MTF. Is it meeting my 40% at 55 line pairs per millimeter requirement nominally? Yes, it is. I look at the manufacturability. Now I'm looking at these, and all of these lenses look very manufacturable. This one may be an issue. We can have a negative thickness if we left this lens alone during manufacturing, because, and I forgot to mention this, my apologies, during the generation process, the blanks that are used for making these lenses are larger. So if you extend this lens out, you'll have a negative thickness. It is impossible to make a negative thickness. They have some workarounds sometimes for the lenses, but that ends up giving you an increase in cost because you have more fallout. So it's just much better for you to make sure that the edge thicknesses are friendly for manufacturing when they're oversized. So another thing I am looking at is what I would call a kink, as in a hose. Normally, you would like your rays to flow very smoothly through the system, but I see this change in slope here is pretty extreme. And in my experience, this leads to sensitivities when I'm starting to do my sensitivity analysis or manufacturing analysis. So, and I can answer that. Yeah, there was the ray angles for this lens had to be controlled to be less than 6 degrees for this particular one. Thank you for asking that question. So here's another lens that I looked at. This one looks a lot nicer. It looks like it performs better when you take a look at the MTF by itself. And the rays look very smooth coming through here. But the large problem that I see here is the second element of this doublet. It is very thin. The rays don't even trace through the doublet here. This negative thickness is not a problem. We can truncate this lens to get rid of that. So the largest problem I have is the second element of this doublet. So what I think I can do is thicken up this doublet, make it larger in diameter, and then take some loss in performance at full field. The way this is tracing, though, I feel like the loss in performance is not going to be that bad. So this is the lens that I'm going to choose to present for feasibility after some tweaking. So how am I going to make this design realistic if it passes feasibility? So we're going to say the lens passes feasibility. It looks like it's something we can do, and now I can move on to the preliminary design process where I make this lens more realistic. How do I do that? Well, I tighten up my constraints for the edge thickness, center thicknesses. The air gaps I allowed to get as small as 50 microns for my feasibility. Now I'm going to push them out to a minimum of 100 microns. Certain customers have preferences for the glass catalogs that you use. So for this one, I was very free with my choice in glass catalogs because I just wanted to see if it was possible. But as I said, certain customers are going to restrict your glass catalogs now. So now it's time to use a specific glass catalog if you haven't been using one already, which now makes your solution space smaller, but hopefully you can find something with equivalence. And then finally, I let the lens be a little bit longer, again, to make my solution space larger. Now I'm going to try to make the lens more compact. After I do all this, and if I come up with a design that looks realistic and meets all my needs, I run the sensitivity analysis to catch any potential problems with manufacturability of the elements themselves prior to using any time in the critical design review. If it has no problems with sensitivity, then we move on to the critical design review, which is where an optomechanical engineer takes a look at my design, puts metal around it. I apply those metal tolerances in concert with the element tolerances and analyze real-world system performance using Monte Carlo generation. So this is the lens that we ended up with for preliminary design review. As you can see, I fixed the issue that we had with this second element. The rays coming through look very smooth, looks a lot better, but we did take a hit in MTF here at full field, which I predicted because it has to go through this glass here. It still very much exceeds what we needed for the nominal performance of the lens. So now I will perform a sensitivity analysis. So for me at Edmund Optics, I know what the tolerances are that we use because I know our manufacturing capabilities. Not everyone has this option. So this is the command to apply the default tolerances. You can put it in the command window so you can do the sensitivity analysis. So this is using the wavefront differential analysis that was discussed earlier. You have to make sure that you're using the correct analysis for your application. For me, MTF was the specification that I'm going to use to determine whether or not this is sensitive. And this is a very important step because, again, it can let you know if there's a possible issue with your design being sensitive from just the manufacturing of the elements and the tolerances applied to them. So one thing to note is this is not an aggregate chart. So because one of these is over 90% doesn't mean that I will have a 90% yield for 55 line pairs, which I'm sorry, I forgot to put that on here, for 55 line pairs per millimeter. What this is each individual field's probability of meeting the specification of 20% contrast at 55 line pairs per millimeter. So worst case scenario would be 0.93 times 0.94 times 0.98. And that is not representative of what's realistic. This is the most pessimistic view, but still this lens looks like it's performing very well. If I had a curve, let's say that was a lot flatter and went up here and crossed 20% at 50% 0.2, we'll say here, at 50% probability, well, then I know I have a real problem with this design. And again, I have to either design out the sensitivities or I have to go back to the drawing board and come up with a new design. So this lens is not sensitive, which means it's able to go to the critical design review. So one of our very talented optomechanical engineers at Edmund Optics will design the housing and the mounting, as I mentioned earlier. I will then write a tolerance file that applies all of them to it. Then we do Monte Carlo runs where they randomly perturb these lenses based off of the tolerances I've assigned to them, to the metal and the elements. And I do an analysis at here 75 line pairs per millimeter for 500 Monte Carlo runs. So 500 individual files were generated and then analyzed. I chose 75 line pairs here because I thought the lens was doing really well, and I kind of wanted to overreach here on the performance. As you can see, up to the 4th urgent sensor, we have a pretty good yield. For this instance, the yield we're looking for were 80%. They vary depending on the customer and the lens that's being designed. But I am getting poor performance, or poor yield, I should say, at 75 line pairs for the full field. But that still doesn't hurt me at 55 line pairs. The 55 line pair per millimeter yield ended up being very good. So now this lens has met performance at full field for the specification of 55 line pairs per millimeter, and it exceeds it for the other fields. So up to 4th urgent sensor, it's up to 75 line pairs per millimeter is what it's capable of. So the lens passes the critical design review, which means we're allowed to do prototypes of the lens and manufacture the lens. So this has been a successful design. So this process that we went through resulted in a manufacturable lens that met or exceeded all criteria here. It's Edmund Optics part number 11321. And this family of lenses ended up winning an award. So thank you guys very much for coming on this adventure with me. And if you have any questions, this is when we'll answer them.
Hi, Ed. This is Dave Hasnauer. So I've got 2 questions from the chat that I'll ask you and you can answer. And then we open it up. If people want to unmute, they can ask questions directly. So the first question was the concentricity controlled with a user-defined constraint to control that concentricity for the wedge tolerance?
Yes, I ended up for concentricity, and for this file, again, I was taught to use the command window for everything, so I write macros using the .seq files. I ended up doing the math myself to control the concentricity in this instance.
Very good. And I did mention to the user, I think I did responded to everyone, that the spec builder window that we have also has a macro for doing that calculation, for checking that. And so if you're looking for sort of the macro code for your own designs, you can check the macro out in the spec builder window for concentricity for kind of monocentric surfaces on an element. The second question was if you can go back to your Monte Carlo slide, I think it was just the last one, yeah. Why is the MTF of all fields end up the same at the 0% probability? So I guess it's the fact that, well, so you might want to explain the
okay, so sorry. So yeah, this is how many Monte Carlo runs were run, right? So then there's nothing at 0, but at the first one here, what I did was I got all 500 Monte Carlos, and then I organized them from the highest percent contrast to lowest. Does that make sense? in order just for me to easily identify, based on this pass-fail line, how many would have passed or failed. So if I just took the data as presented, then these would be a bunch of random dots going everywhere. I happen to sort the data so it's easier for my customer to see, the trend line, if you will, going towards the failure portion.
Okay, and I think that I messed up. Apparently, go one slide further back to your TOR wavefront differential run. So I guess the question is why the MTF all fields end up the same at 0% probability. So this is a cumulative probability. So you're going to have 0% of. I'll answer this since this is a code 5 plot. Is that this modulation transfer function? There's going to be a diffraction limit, and you're not going to have any designs that are going to be above the diffraction limit. So by definition, at the diffraction limit, you are going to have a 0% probability of being above that. And so that's kind of how this sort of ramps up. And then as you apply those MTF degradations. And Ed, if you've got something you want to add to that, but that's, I think the answer to the question is the reason these are all 0 up there by 0.75 is that they're either close to or they can't go beyond the diffraction limited MTF.
Yeah, you've covered it. Thank you very much.
And then another question that just came in is, what was the most sensitive surface for your design based on the sensitivity analysis?
So for this particular design here, and based off the sensitivity analysis, I ended up having some sensitivity around the stop for this particular design. If I had to guess, when I was looking at it, I guessed wrong because that's what I'm talking about now. I was going to think that this was my most sensitive surface just with the setup here and the large variance from the air gap out to this change here. But for this particular design, I ended up having a sensitivity to decentering right about the stop.
Okay, very good. Another question just came in is, how do you calculate the probability that the MTF of all fields is higher than a certain threshold? Are the MTFs of fields uncorrelated?
Can you repeat that?
Sure. I think the answer is yes. That the MTF of the fields are uncorrelated. They're kind of subject to different aberrations. But the question was, how do you calculate the probability that the MTF of all fields is higher, and it says that, but I think it's than a certain threshold. So, as I understood it from your previous explanation, Ed, is you took your 500 trial, you looked at all the fields, and you figured out for every field what the percent of 50% were above a certain MTF.
Okay, yeah, so the explanation to this is what I do is I have the data for every single field, which they're correct about. And I simply just pull the lowest because if any of my field points fails, then that whole lens fails. So you can have one where it performs very well up to, a ½ inch or something like that. But at 4/3 inch, it's not as good. Then that lens is a failure. So all of these are just based off of the lowest contrast percentage for that lens up to the field that I've defined here.
Okay. Another question that just came in is, can you disclose the glasses you use for each of those lenses?
I don't know if I'm available to, but my email, I believe, should be on this, so you can write me and I'll ask to see if that's possible.
Very good. Another question is, the small air gap between elements 5 and 6 problematic for housing?
So this is not the scale. I've smushed it a little bit so it can work. So right now we have glass on glass contact, so it wasn't that big of a deal. I try not to design glass on glass a lot, but this one happened to be a special case. So in this instance, it was not problematic. If you mean between 6 and 7, this is at the very least 100 microns, which we have no problem controlling. So when you get below 100 microns that we have issues. So again, I had to smush this in order for it to fit. So the scale's off, so it looks like this is a smaller air gap than it really is.
Gotcha. Did you consider athermal aspects in this design?
I did not, because that was not one of the requirements for this.
Okay. And what wavelength band did you use for the modeling?
So for the modeling, and I'll go up to the top right quick, we used F, D, and C. And that was this for this particular lens. It would vary depending on the design. This particular one, it's just F, D, and C.
Got it. Okay, so there's no more chat questions that I see. If it's possible that I missed them. Sorry, do you have any slide on the color performance? I don't remember seeing a rim ray or a...
I do not have any slides on color performance of this right now.
Okay, okay.
But
And
yeah, all of my
was,
analysis was polychromatic, though.
Got it. Was stray light analysis considered?
Stray light was not considered for this lens. It was not something that we were worried about for this instance, but we do use best practices when we're doing the manufacturing of these.
Very cool. Okay, and so there may be others that will come in the chat here as we hang on. But if anybody does wish to unmute themselves and ask a question directly, please go ahead and do so now. But please remember to mute yourself once you're done. All right, going once, going twice, and I do have another question on chat. Did you do any ghost image analysis in Code 5 on your design?
I did not for this design.
Okay. And what was the total? What did the total track end up being? Was it at
it was probably about with this lens like 91-ish, 92. I would have to look it up, but it was within the total. Oh, the total track. Sorry, I know the lens length is what I know. I'm not sure what the total track was right now.
Okay, yeah, I missed that as well. So, but again, you have your email, so that user can.
Yeah, I mean, for questions like this, just email me and I can get you guys the information.
Thank you very, very much. Thad, a special thanks to you for sharing this really interesting design with us. And thank you very much for joining us for this webinar. I'm going to go ahead and close out the meeting now. But again, if you have questions, just feel free to email us and we will get back to you.